Well, good morning and welcome then to our third lecture in MFCS. And having begun by introducing what's called propositional logic, today we are going to extend our logical language. By analogy with a programming language, where some of the ways in which you might begin leave you rather limited in the kinds of data you deal with. Perhaps when you first start programming, you only deal with numbers as the only kind of data or something like that. And the things that you can do with them are very few. And gradually you look at more and more programming language. Well, we're looking at a mathematical language rather than a programming one, but we shall extend our idea of a proposition and a propositional variable, first of all, to something a little more powerful, we call predicates. And this involves admitting that there are not just truth values in the world, there are other kinds of values, and sometimes we really do want to talk about them, not just indirectly through truth-valued variables. And the other thing we shall introduce to go with that is a way of ranging over those different values, if you like, the mathematical equivalent of a loop. So there are some things we would like to say that as things stand, we'd have to write down an infinitely long formula to say. And that's somewhat inconvenient, so we'd rather not need to do that. So, predicates and quantifiers. So let's begin by defining with an example what we mean by a predicate. Well, as I've already indicated briefly, a predicate is a bit like a proposition or propositional variable, but instead of just writing P or some other more exciting name, where P is something that is either true or false all by itself, a predicate is a proposition P that is about certain values. Here just shown schematically, value 1, value 2, and there may be a number of different values that this is a truth assertion about. And these things may not necessarily be just truth values at all. They might be more exciting things like numbers or computers or computer programs or whatever it might be that we care about. So we can't just say that P itself is true or false. We say, if you tell me which particular values you've got for these variables, now I have something that's either true or false about them. So thinking back to our earlier examples, rather than having one truth value, one variable that says the vase is silver, and then if we were considering instead buying our aunt a teaspoon or a thimble or a brooch or any number of other objects that might take our attention. And in each case, we have a completely separate logical variable that says, you know, the thimble is silver or the brooch is silver. And then in each of those cases, does it have a hallmark on? Well, that's a bit silly. It's all the same thing. Conceptually, the question is this thing silver or is it not? And it is the thing that we need to specify. So when we plug in vase, brooch, teaspoon, thimble, particular objects in front of us, now we can say, is it silver or is it not silver? Here are some other examples. Suppose in the world of numbers then. So now x is not a truth value, true or false, it's a whole number. Then the predicate even says for any given number, is it even or not? So even of 2 would be a true statement, even of 3 would be a false one. So conversely, we've got the odd predicate. Is x an odd number? And then perhaps we want to know whether numbers are prime. Is x a prime number? And so on. So all of these are predicates, and they are predicates about a single integer variable. Another example, factor. So the idea here is to express the idea x is a factor of y. So 2 is a factor of 6, but on the other hand, 3 is not a factor of 7. So is a factor something that's true or false once we say which particular pair of numbers we're talking about. So that's the idea of a predicate. And I have tried to stress this point already, but let me emphasize it further. These variables can have all kinds of values, whatever sort of world it is we want to talk about as computer scientists. So that would even include, for example, people. Interestingly enough, there have been attempts to try to capture the law, which is largely about people and things they can do and things they can't do. There have been attempts to capture the law of the land in the UK as a collection of logical statements, an extremely difficult and challenging thing to try to do because the law is very complicated. So a tiny fragment of that might be that there are certain statements that might relate people, someone, S, and an age, X, that they may or may not have. So we might say age SX is a predicate where S here is a variable that ranges over people, someone, S, and X is an age in years. So that would be true if S was X years old. And then we might have related predicates. S is an adult, meaning S is at least 18 years old. Okay, so I hope this seems clear now to you. We can generalize the idea then of a simple propositional variable that is by itself true or false to a predicate which is true or false about certain values. Well, when we do that, the need very often arises to talk about the values that we know are out there, whether they are objects we want to buy for our aunt, or whether they're people, or whether they're numbers, or whether they're computer programs. We need to refer to them in some way other than simply plugging one in as the particular value we're giving to a predicate. So if we return to our adult example, well, we want to be able to say somehow, well, of all the ages that S could have, we know S must have some particular age, X, so age SX, and this X is greater than or equal to 18. Or again, suppose we want to talk about a number being prime, well, that brings into our head the idea of all the possible factors it might have. If K is a factor of X, then K equals 1 or K equals X. And I've actually, I point out, made a little slip in that example because we don't want to allow 1 as a prime number, so I guess I really want an exclusive OR. I don't want to include the case where the factor K is 1 and 1 is actually a value of X. 1 is not a prime number. But anyway, despite that little slip on my part, the point of the example is made that we want to refer to all the possible factors that X might have, or here, some age that we know S must have. And that motivates the introduction of our, what is going to turn out, and we'll see this in a moment, to be rather like the power of loops in a programming language. So we're going to have some new symbols now, and they are called quantifiers. And the first one is known as the existential quantifier, and you can read it, there exists. Okay, we write it like this. So the symbol is this one here, and a formula, there exists an X such that P is true of X. So that's a reading of that. There is a value of X which makes P true. So that's there exists, and there's also another quantifier, the so-called universal quantifier, which we can read for all. So that's written using this symbol. So we've got a rather similar looking form of new term or formula that we can write, but this time instead of introducing it with the existential quantifier, let's practice our new terminology, we use the universal quantifier, so we can read this for all values of X, P of X is true. Now there's a little curiosity at this point, and I'm afraid when there are curiosities, I can't help being attracted to them. It will not perhaps have escaped your attention that in referring to these symbols, I strenuously avoided referring to a capital E and a capital A, which might have seemed a little odd because they're clearly derived from those symbols. But here's a strange thing. If you say to somebody, yes, I've begun studying predicate logic now, they may say to you, oh yes, predicate logic, it's got those backwards E's and upside down A's in it, hasn't it? I think that's a very strange thing to say. Why do you think that is? Discuss with your neighbour. That's a slightly sideways one, that. But, I'll come to you in a minute. Okay, so as I say, slightly different sort of question, that one, but I wonder whether anybody's come up with anything. Why is that actually a rather strange thing to say? Any offers? Yes?
Those symbols predate the modern alphabet DNA.
That's a nice guess. Actually, I don't think that's true. So, no, nice guess, but they are based on a capital A and a capital E. But there's something else that I'm after. Yes?
Is it because thinking of these logic symbols in terms of an alphabet is counterproductive because logic exists on a different level to language?
Okay, so in some sense, we need to, when you look at them, you don't want to be thinking, oh yes, that's an A, and that, no, just think logically, just think. Yes, I see the point, and that has some validity, but actually that's not what I was thinking of either, but though thank you. Yes, let's try one more, yes. Okay, yes, that also has some truth in it, so it doesn't have to be that we use these symbols. We could have introduced another symbol. It's not sort of really fundamental. As we've already pointed out, some people use different symbols for and or to those that we are doing. I'm sure there are many other suggestions. Thank you. We've looked at 3. My point is just this. Why invent a complicated explanation when there is a simpler one? So the suggestion is that the E has been made backward, but the A has had something else happen to it. It's been turned upside down. Well, hang on a minute. You have seen these symbols before. Don't tell me you've never read the person's newspaper sitting opposite you on the train and such like. Of course you have. And why is that? Well, because, of course, if you rotate their newspaper, you get this. So both of these have been rotated. So what a strange twist of the human mind that we invent 2 different explanations when we all know perfectly well that there is one explanation, and we have actually seen these symbols before. Isn't that curious? Not really that much to do with maths, but it is to do with your brain and how it works. So the key point I want to draw from that is, don't make explanations complicated when they could be simple. And of course, that is a lesson that I myself as a lecturer need to bear in mind. So, okay, so there you go, these 2 symbols. So if we now go back to our examples of a moment ago, whereas we had at that point to resort to putting words into the middle of our formula, now we don't need to do that anymore. Using the newfound power of the quantifiers, we can say what we said before without resort to just a bit of wording. So adult is true of someone S if there exists an X such that S has age X and that age X is greater than or equal to 18. Or prime is true of a number X if for every k, if k is a factor of x, then k equals 1 or k equals x. And as I say, I've actually made a little slip in that example. We really want exclusive OR so that we don't have 1 as a prime. But the point I'm making is that we now don't need words to express that kind of thing. We can do it using quantifiers in that way. Now, we've been here before in the sense that I've introduced, like rabbits out of a hat, 2 new symbols, and that is the for all and the there exists. And I'm sort of saying, trust me, these are going to be useful, and here they are. And you might think, as we thought before, well, I wonder if there could have been other quantifiers, or we could have had this loopy kind of idea in some other way. Is there any particular reason why you've chosen to introduce these? And the answer is there certainly is a very good reason. Actually, there exists and for all are like a big or and a big and. So they like or chain in one case or an and chain in the other case that if we didn't have these quantifiers would have to be infinitely long. Let's just see that. So the claim then is that there exists and for all are linked to things we've already got, or and. So there exists is like a chain of statements linked by an or. Let's see that. Suppose that we're in the world of positive integers, so that's the world we're saying things about logically, and we want to say then there exists a positive integer x such that p is true. So we can say that now in one little formula, assuming that we know what p stands for. Well, without the quantifier, how could we write that down? Well, as I say, it would be like an infinitely long chain connected with or. P is true of 1, or P is true of 2, or P is true of 3, or, and so on forever and a day. So a there exists statement is like a chain of ors. And correspondingly, a for all statement is like a chain linked by and. So if we want to say every positive integer x has the property p, for all x, p of x is the case, that would be equivalent to saying, wouldn't it, p is true of 1, and p is true of 2, and p is true of 3, and so on, and our formula would have to be infinitely long. So that is where the for all and there exist come from, if you like, or how they link to what we have had before. So that might raise the question, are we going to have a whole lot of algebra? And maybe for some of you that makes you say that with a slight horror in your voice. We're not going to have a whole lot of algebra. We can develop quantifiers and the mathematics of them further if we had the time to, but as perhaps you will be relieved to discover, we don't have a lot of time to do that in this module. What I would like to point out, however, since we've got the link with and or, we've also, therefore, got this nice mirroring property that I'm so keen on. I'll take your question in just a moment. So remember, we've got this very pleasant mirroring property that links and or. And the same idea extends to quantifiers. So if we say here, it is not the case that there exists an x such that p is true of x, that's equivalent to saying, for all x, it is not true that p is the case of x. So we can push the negation inside the formula. The there exists, which is like an or chain, flips into a for all, which is like an and chain, and the not arrives to be applied to each of the tests, the p-tests, that the for all or the there exists could be expanded to if we tried to write them out as a big chain. Now, our friend here had a question, and actually, sorry, I forgot you also had a question a moment ago, or maybe you did. Perhaps it's gone away now. So let's take yours first.
Yeah, what do the commas mean? Where are they from?
Okay, here's one of these. I will always write a comma after there exists X. I will then put a comma in. It will sometimes be helpful to delimit at that point. If you look in some textbooks, they may use another symbol. Some of them use a dot, sort of raised somewhat. Often there's some sort of punctuation symbol following the there exists or the for all, introduce a variable name. So it's just part of my notation whenever we write a quantified formula. Thank you for the question. Did you also have a question?
You answered it.
I've already answered it. Okay, great. So, we've got this nice mirroring property that we can push a negation inside one of these things. The quantifier flips, for there exists becomes for all or the other way round, and the negation arrives on the inside. As I say, if we were going to unpack in more detail, go down to first principles to find the mathematics of quantifiers, it would take us, we could do that, but it would take us rather more time than we have available. So I'll just give you an informal sketch of why that's true. So let's just look at the first of those. So let's look at what that's saying. On the left-hand side, it is not the case that there exists an X such that P is true. Well, that's saying no value of X makes P of X true. That is to say, for every value of X we might try, we will find that P of X is actually false, which is just to say, for all X, P of X is not the case, not P of X. Okay, so this is an informal sketch because I've had to resort to just appealing to your worded understanding here. But these equivalences, these laws, you may take and use as algebraically true equivalences. Well now, these for all and there exist statements, as we can see, are powerful. They're rather like, as I've already indicated, the power of loops in programming, and they, as we've also seen, can, in some examples, replace what would otherwise be an infinitely long formula, just like a programmed loop can, with just one small formula. So clearly they're powerful. Sometimes they're actually too powerful, you might argue. Suppose, for instance, someone says, everyone saw the presidential candidate debates between Trump and Clinton. So they're essentially saying, for all people, right? There's a world of people out there. Every person, X, it is true, X saw the presidential debate. Well, the trouble is that's a bit too strong, isn't it? I mean, some people were asleep, some people are just not interested, so we start wanting to restrict. Oh, well, just a minute. All American citizens who were watching TV tuned in to watch the presidential. Well, that may or may not be true, but it's getting closer to the truth. So you can see that a for all statement, if we leave it completely unrestricted, sometimes says a bit too much. On the other hand, a there exists statement says somewhat too little. So I might say to you, did you know there is someone who won the national lottery last month? And you sort of think, yeah, I suppose there is, I knew that, I know there's a national lottery. That really doesn't tell me very much, Colin. But suppose I say to you, did you know there is someone in this room who won the national lottery last month? Now you start glancing around to see which of your fellow students is wearing a Rolex watch, because you think, well, okay, yeah, that's obviously telling you a lot more. So whereas the for all, left unrestricted, says rather too much, and we may want to narrow it down a bit. There exists left unrestricted says perhaps rather too little, and we make it stronger by narrowing it down a bit. Okay, so the good news is we do not need a lot of extra new squiggles. We've already got, to do this, we've already got what we need. So we can have a predicate symbol, R. I've used the name R to indicate a restricting kind of predicate, okay? So it's the X's for which R are true. So in my first example, R might be, well, they're American and they're watching television, okay? And in my second example, it's conveniently R for they're in this room, okay? So suppose we want to say, not for all X, P is true of X, but the more cautious statement, well, for all X that satisfy property R, well then they satisfy P of X. Or similarly, there is an X of which Q is true, not terribly strong statement, but no, there is an X of kind R, satisfying property R, and Q is true of this X. Now there's a little mystery here. All of this is the case, and that's so the good news is we don't need new kinds of squiggles. We've got already enough squiggles, we've got enough stuff in our logical language to be able to express that kind of thing. But there's a slight puzzle. Because of this mirror property, if everything was working really nicely, I mean, and for all and there exists are mirrored, and, oh, but and or are mirrored, and so that's rather odd. If this is and, that implies, of all things. That's a bit puzzling. Why is that then? Discuss that with your neighbour. Okay, so the nub of the question is, whatever happened to the mirror, and has anybody got any suggestion of an answer? Whatever happened to the mirror? Yes.
I don't really know, but is it anything to do with that chain rule that you were talking about?
Okay, an honest admission there if you didn't hear. You said, well, I don't really know, but maybe it's got something to do with chains or something like that. Okay, no, I don't think you're quite on the case, but I like your honesty. I don't really know here, but I'm just throwing one out. Yes?
You could get or if you translate the equation into not R of X or P of X.
Okay, that's what I was fishing for. We're not so far away from what we'd expect in the mirror after all. Remember, and implies, we've got that little translation rule, which says Rx implies P of X is equivalent to not Rx or P of X. So the first one is Rx is not the case or P of X, and the second one is Rx is the case and Q of X, okay? So they're not quite so far away from the mirror idea as it first appeared. Let's be quite clear that it does matter. You can't just say, oh, well, you write an and or an implies. You know, one of those, you just write something in and it restricts it. No, it does matter. Let's just see that in some quick examples. So here's some simple examples. So practicing the idea, we might like to say everyone is intelligent, and I'm not being mean enough to suggest we might not want to say that, but certainly, and especially in present company, I would like to flatter you by saying, well, every student is intelligent. So for all X, if X is a student, well, then X is intelligent. I'm very happy to make that statement. Wouldn't be quite so keen to make the next statement. This says there is someone X, not just someone in general who is asleep, but specifically there is someone who is a student and is asleep, which at this time of day would of course be deeply shocking. So that says some student is asleep. Okay, you see the idea. So just to push this home, notice that would not at all be the same as saying those things but with the and the implies exchanged. So this one, for instance, where we're saying something rather like this top case, but whoops, we've mistakenly, instead of writing the implies here, we've exchanged that for an and. Notice we're now saying something quite different. We're now saying everyone is a student, which we look out in the real world, we know that they're not. Everyone is a student and is intelligent, which is not at all saying this. So you have a go. The other one, suppose I swap around in that case. A moment ago, we saw that this means an informal and English reading of this would be some student is asleep. What does this thing down here mean? And I warn you, it's tricky. I can't think of a short way of saying that in English, but have a go. Talk to your neighbour. What's your best effort to say that in English? Okay, natural lull. Any offers? Anybody have it? It is tricky, so don't worry. If it comes out a bit, scrambled, make your best effort. Yes?
Some values of X are students, but if X is a student, they're definitely asleep.
I don't think so. Nice try, but I don't think that captures it. Yes?
If there is a student, then they are asleep. So there might not be a student.
Okay, be careful. That sounds like a general rule. If there's anybody out there who's a student, that means they're asleep. That is saying for all X. X a student, X asleep. This is saying there is an X for whom, I think that your solution is close, but it confuses are we saying this is a general rule, or just there's one particular case where this might be true? Let's try somewhere else. Yes, at the back.
There exists someone who is not a student or is asleep.
Okay, that's fine. That captures it because of the reading of the implies. So, as I say, I can't think of a short and simple way of capturing this in English. What I've got written down here is quite similar to what our colleague has offered from the back. So we can sort of write this down. Student X implies asleep. Use, as you did, the translation rule, turn the implies into a not and an or. So, and then we could use De Morgan's rule here. So we get, there is somebody for whom it's not true they're a student and not asleep. So you could arrive at something like this. There is someone who's not an awake student. As I say, not very snappy. But the key point is, it's certainly not saying just the same as this example up above, which says some student is asleep, which is a quite different statement. Okay, well, remembering the handiness of the mirror principle and the De Morgan rule that goes with it, that captures it, what happens if we throw in restricting predicates? These little extra R conditions, like someone in this room, or someone who was American and watching TV, and so on, or someone who is a student. If everything's working properly, then the De Morgan rule should still work, even if there are restrictions involved, and of course the restrictions should be preserved. So we expect, and I know this looks a little complicated, but it's not as complicated as it might seem at first. It's just the De Morgan rules for the quantifiers, just as I showed you them before, but now we've got, in addition, the Rx and, in the case of the there exist, or the Rx implies the restriction part in the for all, and similarly in the second case. So we would expect that if the mathematical machinery is working correctly, those equivalencies would hold. Do they? Well, you will, I'm sure, be delighted to know that this gives us an opportunity for an outing of the green window. Yes. Okay, so if we look at the left-hand side in the first case, we saw the basic rule that the De Morgan principle, the mirror principle, can apply to the quantifiers. So we've got not there exists an X such that something or other. So using the basic rule that we saw before, and I called it Theorem 7, we can push that not inside the there exists, it flips into a for all, and the not arrives on the inside. So that's all we've done so far. But now look, we've got something of the form a not applied over an and of two things. So we can use the plain and simple De Morgan's law, just about and or, to turn not Rx and Px into not Rx or not Px. But now we can use implies translation because we've got not Rx or. Okay? So that's Rx implies. And sure enough, as we wanted, we've got for all x, Rx implies not Px. So that is the first side. Yeah, I mustn't stay with it too long because I don't want to keep you late. I think glancing at the clock, we can probably afford a brief pause on this. See if you can persuade your neighbour what a similar proof of the other one would look like. We'll take a minute on that. I'll show you that. Okay, let's move on. Not the sort of thing it's easy for you just to call out, obviously. So I'll just show you a very similar proof, essentially. So assuming that you were trying to do that rather than just taking a little break, which is also fine, again, you apply plain and ordinary theorem 7, the idea that you can push the not through there exists and get the for all and vice versa. So plain and ordinary rule for doing that. And again, you use implies translation, and again, plain and ordinary De Morgan, just flipping a negated and into an or and vice versa, with the negation arriving on the inside. So it's a very similar proof, which again can be done in 3 steps or so. Okay, there's one last thing that I want to draw your attention to, although, as I say, we won't be working into a kind of full-blown algebra of quantifiers. There's another thing that does occur, which is rather like you can have nested loops in your programs. Many of you perhaps will have been programming since you were knee-high, so you've written lots of nested loops. So sometimes we get nested quantifiers, and there's a little point that can catch people out. So the rule, the question that arises is, can we swap the loops? You've perhaps played this game. If you've done a bit of programming, you have an outside loop and you have an inside loop. And for some reason we needn't go into right now, you think, oh, I think actually I'd like the program better if that inside loop became the outside loop and the other way around. Sometimes you can do that to advantage, sometimes you can't. In the same way, in our logical formulae, suppose we're saying something like, here's the first case, well, there is an x such that there is a y such that pxy is true. There exists, they're like. They're both, there exists. So it's perfectly fine to say that the other way round. There exists a y comes first, there exists an x comes second. That's fine. In a similar way, for every x, for every y, pxy is the case. You could say it the other way around, it would say the same thing. For every y, for every x, pxy is true, also true. But the one to be careful of, because this is not valid, is you cannot flip them if one is a there exists and the other is a for all, or the other way around. It is not valid to flip them around. And this little illustration, hopefully, will show you why not. Suppose that we map out our world of values as a grid. So here are the possible values. Of course, there may be many more possible values of y and x than just 3 and 6 or whatever I've allowed. You can imagine a much larger grid. But let's see what's happening here. The first case says there is an x such that there is a y and so on. Right, there is an x, in other words, there is some column in which there is some row where p of x is true. So I'm up to my old tricks again with my high technology bits of cardboard and paper. So there you go, that's what that's saying. For instance, saying, well, somewhere there is a column in which there is a row where p is true. Well, we could equally have said, of course, well, there is a row in which there is a column. It happens to be this one where p of x is true. So it's saying the same thing. The second case, B, is saying for all x, in every column, in every row, p is true. Well, that's just the same as saying in every row, in every column, p is true. We've got that picture. It's just saying everywhere. Here's the tricky one. In case C, on the left-hand side, it's saying there is a column, there is an x, in which for every y, for every row, Pxy is true. So it might be this one, for instance. There is a column, there might be more than one, but there certainly is a column in which for every y, P is true. So on the left-hand side, that's a picture of what we're saying. But on the right-hand side, what we're saying is, for every row, y, there is a column, x, for which P is true. But it doesn't have to be the same one in each case, okay? So it might be that that's true, but then it's this one over here that's true, and then this one is true. So that's a picture of what's going on the right-hand side, of when the right-hand side is true, the picture could look like this. And we don't have one complete column at all. So be careful. In this case of the unlike quantifiers, you cannot flip them around. You are changing the meaning. And hopefully that little diagram will help you to see why that is. So as we wrap things up, not an exhaustive summary, but briefly some of the main points. We've extended our logical world with predicates. What are they? Well, we're still writing truth-valued formulae, but they're now about values that we've introduced and given variables for and we're talking about. They can be of any kind we want. We've introduced the quantifiers for all and there exists, and we've seen that they're like giant and or statements. And there are other things I could highlight, but the particular thing I've chosen is this last point because it does catch people out. Remember the rule, like quantifiers, there exists, or for all, you can flip. But unlike ones, you cannot. Thank you for your attention. I'll see you later. Hi.
Hi, just a quick question. Basically, I find it a bit difficult. So one thing to do is
Yes.
just practice a bit more.
Yeah. I mean, how did you get on with the first week's problem sheet?
Okay, yeah.
Yeah, I mean, you know, if when you're in a lecture, you find yourself thinking, you know, I need to think some more about this. That's okay, that's normal, all right? Yes, I'm probably, things go by sort of once, as it were, and that's right. And we're not going to sort of talk about that again and again, which is perhaps the way things are done more at school. No, that's the lecture. But the idea of the problem classes is not that you should arrive, you know, you're already fully up to speed. Right, I can do it all, bring it on, you know, I can solve anything you throw at me that's got, for instance, quantifiers in. It's, no, okay, so now let's practice those ideas. Let's get comfortable with those ideas. So that's absolutely fine, and you needn't, hopefully, I don't sort of utterly puzzle you, but if you arrive at the end of a lecture and feel, well, right now, you know, I don't